Geohash is a latitude-longitude geocode system invented by Gustavo Niemeyer when writing the web service at geohash.org, and put into the public domain. It is a hierarchical spatial data structure which subdivides space into buckets of grid shape. Geohashes offer properties like arbitrary precision and the possibility of gradually removing characters from the end of the code to reduce its size. As a consequence of the gradual precision degradation, nearby places will often present similar prefixes. The longer a shared prefix is, the closer the two places are. Service. The purpose of the Geohash.org service, launched in February 2008, is to offer short URLs which uniquely identify positions on the Earth, so that referencing them in emails, forums, and websites is more convenient. To obtain the Geohash, the user provides an address to be geocoded, or latitude and longitude coordinates, in a single input box, and performs the request. Besides showing the latitude and longitude corresponding to the given Geohash, users who navigate to a Geohash at geohash.org are also presented with an embedded map, and may download a GPX file, or transfer the waypoint directly to certain GPS receivers. Links are also provided to external sites that may provide further details around the specified location. For example, the coordinate pair 57.64911, 10.40744 produces a slightly shorter hash of U4POUIDQQVJ, which can be used in the URL http geohash.org/ U4POUIDQQVJ, uses. The main usages of Geohashes are, as a unique identifier. Represent point data, for example, in databases. Geohashes have also been proposed to be used for geotagging. When used in a database, the structure of Geohash data has two advantages. First, data indexed by Geohash will have all points for a given rectangular area in contiguous slices. This is especially useful in database systems where queries on a single index are much easier or faster than multiple index queries. Second, this index structure can be used for a quick and dirty proximity search. The closest points are often among the closest Geohashes. Example, using the hash ACE42 as an example, here is how it is decoded into a decimal latitude and longitude, decode from base 32. The first step is decoding it from base 32 using the following character map. This operation results in the bits 01101 11111 11000 001000010. Assuming that counting starts at 0 in the left side, the even bits are taken for the longitude code, while the odd bits are taken for the latitude code. Decode binary to decimal. Each binary code is then used in a series of divisions, considering one bit at a time, again from the left to the right side. For the latitude value, the interval -90 to +90 is divided by 2, producing two intervals, -90 to 0, and 0 to +90. Since the first bit is 1, the higher interval is chosen, and becomes the current interval. The procedure is repeated for all bits in the code. Finally, the latitude value is the center of the resulting interval. Longitudes are processed in an equivalent way, keeping in mind that the initial interval is -180 to +180. Finishing the procedure should yield approximately latitude 42.6 and longitude -5.6. Worked example. Here's a worked example decoding 101,111,1001 into 42.6. To start with, we know the latitude is somewhere in the range of 90 to 90. With no bits, we'd have to guess the latitude was 0, giving us an error of a plus or minus 90. With one bit, we can decide whether it's in the range of 90 to 0, or 0 to 90. The first bit is high, so we know our latitude is somewhere between 0 and 90. Without any more bits, we'd guess the latitude was 45, giving us an error of a plus or minus 45. Each subsequent bit halves this error. This table shows the effect of each bit. At each stage, the relevant half of the range is highlighted in green. A low bit selects the lower range, a high bit selects the upper range. The last column shows the latitude, simply the mean value of the range. Each subsequent bit makes this value more precise. The numbers in the above table have been rounded to 3 decimal places for clarity. Final rounding should be done carefully in a way that. So if rounding 42.605 to 42.61 or 42.6 is correct, rounding to 43 it is not. Limitations. One limitation of the Geohash algorithm is in attempting to utilize it to find points in proximity to each other based on a common prefix. Edge case locations close to each other but on opposite sides of the 180-degree meridian will result in Geohash codes with no common prefix. Points close by at the north and south poles will have very different Geohashes. Two close locations on either side of the equator will not have a long common prefix since they belong to different halves of the world. Put simply, one location's binary latitude will be 011111, and the other 100,000, so they will not have a common prefix and most bits will be flipped. This can also be seen as a consequence of relying on the Z-order curve for ordering the points, as 2 points close by might be visited at very different times. However, 2 points with a long common prefix will be close by. In order to do a proximity search, one could compute the southwest corner and northeast corner of a bounding box and search for Geohashes between those two. This will retrieve all points in the Z-order curve between the two corners, which can be far too many points. This also breaks down at the 180 meridians and the poles. SOLR uses a filter list of prefixes, by computing the prefixes of the nearest squares close to the Geohash. 1. Thirdly, since a Geohash is based on coordinates of longitude and latitude, the distance between two Geohashes reflects the distance in latitude-longitude coordinates between 2 points, which does not translate to actual distance. See Havoisian formula. Example of non-linearity for latitude-longitude system. At the equator the length of a degree of longitude is 111.320 km, while a degree of latitude measures 110.574 km, an error of 0.67%. At 30 degrees the error is 110.852/96.486 equals 14.89%. At 60 degrees the error is 111.412/55.800 equals 99.67%, reaching at the poles. Note that these limitations are not due to geohashing, and not due to latitude-longitude coordinates, but due to the difficulty of mapping coordinates on a sphere to two-dimensional coordinates and the difficulty of exploring a two-dimensional space uniformly. The first is related to geographical coordinate system and map projection, and the other to Hilbert curve and Z-order curve. Once a coordinate system is found that represents points linearly in distance and wraps up at the edges, and can be explored uniformly, applying geohashing to those coordinates will not suffer from the limitations above. While it is possible to apply geohashing to an area with a Cartesian coordinate system, it would then only apply to the area where the coordinate system applies. Despite those issues, there are possible workarounds, and the algorithm has been successfully used in MongoDB, HBase, and Accumulo to implement proximity searches. An alternative to storing Geohashes as strings in a database are locational codes, which are also called spatial keys and similar to chord tiles. License and patents. The Geohash geocode has been put in the public domain by its inventor and the public announcement date, on February 26, 2008. While comparable algorithms have been successfully patented and had copyright claimed upon, Geohash is based on an entirely different algorithm and approach. See also, Geohash 36, grid, Morton number, natural area code, Maidenhead locator system, military grid reference system, external links, geohash.org, visualizing Geohash, Clojure library for encoding and decoding Geohashes without calling geohash.org, Perl module to interact with geohash.org, Java classes for encoding and decoding Geohashes, Geospatial, Geohash, Geohash Java, and JavaScript module for encoding and decoding Geohashes without interacting with geohash.org and demo, MySQL function for encoding and decoding Geohash, PostGIS function that returns a Geohash representation of a geometry, RubyGem for encoding and decoding Geohashes without interacting with geohash.org, Perl module for encoding and decoding Geohashes without interacting with geohash.org, PHP class for encoding and decoding Geohashes without interacting with Geohash.org, Python module for encoding and decoding Geohashes without interacting with Geohash.org, Haskell library for encoding and decoding Geohashes without interacting with Geohash.org, C library for encoding and decoding Geohashes without interacting with Geohash.org, Go package for encoding/decoding Geohashes to UTM-lat/long, Objective-C library for encoding and decoding Geohashes without interacting with Geohash.org, OCaml module for encoding and decoding Geohashes without interacting with Geohash.org, KML file for Google Earth displaying Geohash grid, Geohash, Node.js module for encoding and decoding Geohash, a Geohash implementation in pure Ruby, area check tool, 2, GeoMeasure, a spatio-temporal database using Geohashes and Accumulo, references.